Okay, we are going to carry on with the last slide now. Okay, I just want to complete the last slide. I hope that after you watch this and then next class we will carry on with the second part of electrodynamics, and then we will focus on motors and generators. So let's look at this slide together. Okay, so currently what we are trying to do is we are going to talk about induced current, which means produced current, and then we are going to identify the direction of current. Okay, if you remember, for the direction of poles of an electromagnet, if you look at the right hand side here, can you look at your right hand side? So you see that if you use your other fingers, okay, these are the other fingers direction, imagine that, okay, that is showing the direction of electric current, and your thumb is going to show you the north pole, okay, and then as you can see, this side is going to be like north, this side is also going to be like south, okay, and then we are going to use this same right hand rule to be able to identify the direction of induced current, okay, direction of induced current. That's all we are going to do today. So how do we identify direction of induced current? We use right hand. As a bar magnet moves into a solenoid, okay, can I just clean up here? As a bar magnet moves into a solenoid, the needle of a galvanometer is deflected. So which means that the needle is changing direction, which means we discussed this, and the electric current is produced, potential difference is produced and deflected away from the zero mark. So which means that there is a current coming up. As the bar magnet is removed, the needle deflects in the opposite direction. So which means that when you move it in, as you can see in the second diagram, okay, when you move it in, this is the direction of electric currents. Can you see the direction of electric currents here? Okay, this is what we can call as anti-clockwise direction. If you look at one of these circles, that's anti-clockwise direction. And then in the second one, when you move the magnet away from the solenoid, okay, and then what will happen? The direction of current is opposite. It's going to be opposite. It is what we call clockwise direction, okay? And the magnetic energy is converted to electrical energy. So which means that I use magnetic energy and then I produce magnetic field, I produce electricity, electric current, potential difference. That's what we call as induced current, generated current. That's what we call as induced EMF, that is generated produced EMF, electromotive force, okay? That's what we use as another name, we can say for now, another name of potential difference. The direction of induced current can be determined by using Lenz's law, okay? What is Lenz's law? States that the induced current flows in one direction so as to set up a magnetic field opposed to change in magnetic flux, okay? I'm just going to discuss this. We don't have to know Lenz's law, okay? We just need to know how is this direction is created, because later stage, okay, in the next slides, when we talk about generators and motors, we are going to use for Fleming's right-hand rule for motors, generators, and Fleming's left-hand rule for motors, and then we are going to find the direction of current easier, okay? I'm just going to conclude this, okay, the grade 11 part. So which means that if I move the magnet in, according to the Lenz's law, okay, the current will produce to oppose the change in flux. So to oppose. So when it goes into the solenoid, look at the second diagram, okay, this one. When you move it in, what will happen? Okay, there will be, when it comes close, there will be more magnetic lines going through inside of the coil. So magnetic flux increases. So the current is going to produce to oppose this. So which means that, okay, the solenoid is going to behave like a magnet, but to be able to do the opposed motion of the magnet, okay? So which means that if magnet is coming close, and then the coil is going to behave like an electromagnet, okay, as a result of current produced, and then it's going to do the opposed. So when it is coming close, and then the electromagnet in the solenoid, okay, is going to push it back, okay? So when if it is pushing back, as you can see, the north pole is facing the solenoid, so which means that the same poles, like poles, repel each other in the magnets. So this side of the solenoid is going to behave like North Pole. This side is like a South Pole. So by using this, if you use your right hand thumb, okay, if you put your thumb in this direction, okay, and then other fingers, they are going to show you the direction of electric current produced. So it's going to give you, okay, it's going to give you anti-clockwise direction. Okay, look at the first diagram, please. Okay, I'll clean up here. So now in the first one, what do you do? I'm talking about this. Okay, look at this one. Okay, when you are moving away, so according to Lenz's law, this, okay, solenoid is going to create induced current that will do the opposite motion, okay, oppose the motion of magnet. So if it is moving away, it's going to move it close, okay? So which means that it's going to create a magnetic field. How it will create a magnetic field in the red direction, and then if this side of the magnet, okay, permanent magnet is north, and this side of the solenoid is going to behave like a south, and then they will attract each other. It will push it on this direction, okay? And this side is north. And then if you put your thumb, okay, right hand thumb on this direction by using this hand, okay, this way, and then you are going to see that other fingers, can you see the direction of fingers here? Okay, your fingers direction is going to be like this, okay? Your fingers direction is going to be like this. So that's going to show you the clockwise direction, okay? That is how we can use Lenz's law to be able to identify the direction of current, okay? That's what we need to know now. When you push it in, okay, it will push out. When you pull it out, it will push it in or attract back, okay? And then it will create a induced current, and then that induced current can produce an electromagnet to oppose the motion of the magnet, okay? To oppose the change in flux, okay? That's what we call as direction of induced current by using your right hand rule, okay? There is another right hand rule, don't worry, okay? Just learn these two diagrams, okay? There's another right hand rule, simple one, easy one that we are going to use in generators, and we are going to do more complicated examples to be able to show the direction of electric current on a solenoid, okay? So thank you very much. I'm going to end up here. What we discussed until now, I just want to highlight, okay, what we discussed until now. We talked about, okay, conducting wire, current carrying conducting wire produce a magnetic field. So which means that if there is electric current, that's what we call conventional current that you supply by a battery, for example, okay, that goes through solenoid and it turns solenoid into a magnet, okay? That's what we call electromagnet. It produces magnetic field around it. And then we said, can we do the opposite of this process, okay? Which means using electricity producing magnetic field. Yes, we can do by using a magnetic field, which means change in magnetic field. We can produce electric current. That's what we call induced current. And if we produce potential difference, that's what we call induced potential difference. And that's what we call electromagnetic induction, okay? And then we said that to be able to understand the amount of current produced, induced, or amount of potential difference produced, induced, it depends on two quantities, okay? Actually three quantities. The one is flux, okay? Flux depends on the magnetic flux density in Tesla, like strength of magnetic field, we can say basically. And A is the cross-sectional area, and theta is the angle between the normal to the cross-sectional area and the direction of magnetic field. And then we said that if you change the direction of, if you change the position of, okay, coil inside of a magnetic field, okay, constant magnetic field, what will happen? You will change the flux. When you change the flux, what will happen? Induction of electric current. You will produce electric current, okay? And the Faraday's law tells us about the amount of potential difference produced, induced, EMF induced in another way, is directly proportional to the rate of change of magnetic flux. And we said the rate of change of magnetic flux is delta flux over delta T. So if the delta T is shorter, that will be more EMF produced, more potential difference produced. If N, if you look at N, okay, capital N. If there is more number of turns, there will be more potential difference according to formula. If there is one of these quantities in flux is getting higher, there will be more flux and there will be more change in flux. And then in that case, there will be more potential difference. As you can see on the left-hand side, we are not dealing with calculations on these two formulas. We just need to know relationship between these quantities. And then we said that increasing induced EMF, how can we increase the induced EMF? By increasing the rate of change of magnetic flux, by turning the coil faster, decreasing the time, okay? These are all three same thing, okay? And increase the number of loops, which is directly proportional according to the formula. Increase the strength of magnetic field, it will increase the B, it will increase the flux, and then it will increase the delta flux, and it will increase the EMF. Increase the surface area of the loops, it will increase A, and then A is the cross-section area, and that is directly proportional to flux. It will increase the flux, and then increase in flux, it will increase change in flux, and that one will increase the EMF. And then by looking at the change in angle between the normal line to the cross-section area and the magnetic change in the magnetic field lines, and then you can also talk about increasing the electric field. Okay, we talked about the environmental impacts of overhead cables. Okay, and then we said that by using Lenz's law, we can find the direction of, by using the right-hand rule, thumb rule, we can find the direction of induced current. And then what happens is that Lenz's law states that the induced current flows in a direction so as to set up a magnetic field to make up an electromagnet, that field that oppose the change in magnetic flux. So if you move it close, and the magnetic field, okay, produced in the coil will move it away, okay, push it by using north-north facing on the right-hand side. If you move it away and by producing electric current in the solenoid will produce an electromagnet, it will pull it back, okay, to the opposite direction of motion of the magnet, and then which means that the direction of current will be clockwise direction. Okay, that's all for today. Thank you very much.